All right, dealing with polar coordinates. Once again, that should be review for you, and dealing with important polar coordinates. Dealing with conversions from polar to Cartesian, Cartesian to polar. That's tends to be a little bit more. Students tend to have to apply themselves and work at that a little bit more because that's something that's a little bit newer. We did a little conversions when we were in trig class, but not much. Questions you have about anything in regards to the polar coordinates, conversions, polar to Cartesian, Cartesian to polars, graphing polar coordinate system. Once again, provide the solution, so hopefully if you struggle with something, you can sit there and maybe look at what a solution would look like and maybe figure it out from there. Sort of a self-teach type of thing. But that's sort of what you do when you're in college. Your applications in regards to college, yes, you go through what you have in notes, but most of the time you're teaching yourself in college. You have to figure things out. That's what they want you to do. And if you don't want to put the time into it, then they start weeding people out of college courses. But questions you have, things you'd like me to go through. Yeah. Problem number 2. We want to graph r equals 3 sine of 3 theta. Once again, a lot of this will be a calculator exercise for you. And there's no easy way of going through except for doing your theta r chart. Now, if you go 0, 30, 60, 90, 120, and you start plugging into your calculator, well, once again, you can do one of two things. You can make a table on the chart if you want to. And once again, it's a, if you can continue to plug in your values of theta and solve for r if you want to, or if we go back to what we have dealt with before, if we go into your y equals, and in your y equals, type in your, is it 3 sine 3, and you can leave it as x. Is it 3 sine 3x? 3 theta? All right. Now, what you need to make sure of, though, is in your mode, you're in a degree mode. Okay, you're in your degree mode here. Now, we can use a table also in our calculator. Our calculator will do nice things for us. If you go to second and window, which is your table setup. Your second and window, which is your table setup. I want to start at a value of 0. I want to delta table. This means how much you're going up to get to the next value. So if I put a delta table as 10, I'm going to go 0, 10, 20, 30, 40, 50. Well, what I want to do is I want to go up every 30 because I don't want all that other stuff in there. So that's going to tell me to use my table, and I'm going to go up 0, 30, 60, 90, 120, and so on. Okay, once I set up my table, I then go to my second or my table button, which is above my graph. So I hit my second in my graph, that gives me my table. So it gives me my values 0, 30, 60, 90, and so on. But what you see is occurring here is I go from 0 to 3 to 0 to -3, 0 to 3, 0, and to get beyond 180, all I have to do is use my down arrow. I use my down arrow, I go 210, then 240, then 270, and so on. So your table, rather than having to click it like your calculator, your calculator does so many nice things for you that if you don't practice, you don't look into it, you don't realize all the things that your calculator will do for you. So you have to continue to practice using the calculators and the tools. Well, the problem you run into here is you go from 0 to 3 to 0 to -3 to 0 to 3, 0. So you continue to go with your graph. This is a situation where I'm going from 0 to 3, 0 to -3. So I just continue to do this. I just go in, out, in, out, in, out, in, out, in, out. And I don't get any other values. When you have that situation, you need to come up with some other points. That's where your 15s will come in. Well, the nice thing about your calculator, once again, I can go back to my second and my table setup. I can go back to my 0 here, but rather than 30, let's change it to 15. Now when I go to my second and my table, now I have 0, 15, 30, 45, 60. I have those values. And I don't have to plug into my calculator each and every time. KYC. Know your calculator. Saves you a lot of time. When you have functions that you had to find values for, that table value is such a nice thing to do. I use it. I use it as much as I can. Or I use, if I have a long polynomial function, I have to look at values for that long polynomial function. I sit there and I plug it into my calculator and I just type in and calculate a value from my calculator without having to plug in -2 to the 4th power plus 5 times -q squared plus 5 times. I don't want to plug all that in because I'm lazy in regards to, okay, I got to hit this button here. Then I got to remember, because then what will happen is if I go to my exponent, what inevitably I do when I go to my exponent, I forget to use the right arrow and pull myself out of the exponent. So the next thing I know, I have 5x squared, well, or 5x to the 4th, and x is a value of -3. So I hit my caret, and then I go -3. So I have 5, -3 up here. Then I forget to use my right arrow, and I want to multiply this by a value of 7x squared. Well, this ends up times 7x squared times, and everything ends up on in my exponent. That's frustrating to me. Okay. So I use my polynomial value function, my calculator. But what should happen with these intermediate values? With these intermediate values, you'll get what is called a 3-legged rose. Okay, so you get 3 petals. 3 petals that you will come up with. But once again, need to know some of the specifics to your calculator. We have talked about this in trig class. We went through the trig class. We don't use it that much, but this is a nice time to go back to it, so you're not sitting there plugging in value after value after value after value. And what you should get is you should get a 3-leaf rose. I think you go out. I think you'll end up from here. You'll go out here. You get your bunny rabbit ears here. Get your bunny rabbit ears going out to the sides and then down on the bottom on the 270 axis. Other questions? All right, today, as promised, we get to venture into the Barney world. I know, don't give up my name. Now, let me ask you this. See, I know how worlds have changed in regards to when you were little and growing up, and survival techniques of parents sometimes is they plop something that's very, very enjoyable to younger children on TV, that they can sit there and have TV stuff, TV time, and also play with toys. So they have a little bit of, parents have a little bit of peace and quietness a little bit, so they're not having to entertain their little 2-year-old and 3-year-old all the time. So I get that and I understand that. Was Barney still prevalent when you were growing up? Did some of you venture into the Barney world and Baby Bop and BJ and, okay, because that is starting to go away, okay? It's now a little Baby Bum, it's little, it's all those types of things. It's the dancing fruit that goes all around. Okay, it's the world has changed. Where my granddaughter, Barney's not even visible anymore. Okay, not even visible anymore. Bluey's there. Bluey's a big thing, and I like Bluey. Peppa Pig,
What is Bluey?
Bluey. It's an Australian dog that has a dad and a mum. And you have little sister Bingo.
Right. Is that Blue?
And then you have Bluey, of course. No, Bluey's red.
Wait, is
Bluey's red. We're going to call him Bluey, but he's red.
Is Clifford still a thing?
Clifford is nowhere existing
Really?
either. Yeah, Clifford the big red frog is no longer there.
I thought it was a dog.
In your world, it might be a dog. In my world, it was a frog. Okay, because in your word, blue is red, and in my world, blue is blue.
I got you.
Yeah, Clifford's no longer there. Did you guys have Arnold? Hey, football head Arnold.
Charlie Brown.
He had Arnold. He had the football head Arnold. Trying to think of some of the other ones that were there. Curious George. Curious George is still there. Curious George. PBS is still maintaining Curious George.
What about Wild?
Dinosaur Train.
What?
Dinosaur train? That's good.
Thomas?
Thomas Thomas the Tank Engine?
Yeah.
Yeah, Bob the Builder was a big one. Did you guys have Bob the Builder?
Oh, yeah.
That was like a favorite one.
Oh yeah, Bob the Builder was pretty cool. I like Bob the
Little Bill was my favorite.
Well,
Oh,
I know we're enjoying living our fond memories of our childhood. I'm glad I can rekindle a little bit of that. But we get to venture today into the Barney world with respect to numbers. The imagination world of numbers. But we have to go back and review some topics and some ideas and properties of radicals. Okay? When we have the square root of two things being multiplied together, okay? The square root of a times b. This is equal to the square root of a times b. We have them multiplied together, known little radicals. We can bring them together in one radical. This is also true when we have division. We can separate into their own radicals. And both these properties go in both directions. What we cannot do, a big no-no, square root of a plus the square root of b does not equal square root of a plus b. When we have addition in there, we cannot bring them together into addition. Okay, it does not work, or subtraction. Okay, but when we have multiplication division, we can bring them together. Well, going back to the idea of simplifying radicals. If you have a solution, you do a test or whatever, and you solve an equation, and you come down to a solution as 3 over 6. Okay, which is probably a correct solution. But we would like that to be reduced down to a smallest common fraction. We would like to reduce our fraction down. So leaving a fraction as 3 over 6 is probably a little bit more inappropriate, where we would want to reduce that down to what? 1/2. So leaving a solution or fraction as 3 over 6 is not very proper. We should reduce that fraction down to 1/2 or 1/2. While leaving radicals in unsimplified form is also not quite as accepted as, is not quite as accepted. We want to be able to reduce our radicals down also. Well, how we reduce our radicals down is by utilizing this property right here. If I have two things being multiplied together, I could separate into their own radicals. Well, when we separate, or when we try to figure out, we have the square root of 24 there. We want to reduce that down. Okay, we don't want to give a decimal, 4.98732. We don't want to give that decimal there. We want to just simplify it down. Well, when we go to simplify it down, what we want to do is we want to break it down into two things that we can multiply together to get the value 24. Well, we have 1 and 24, we have 2 and 12, we have 3 and 8, we have 4 and 6. We have a bunch of options to break down 24 into things that we multiply together. But what we want to be able to break it down into is one of these factors that we have up here. We want one of those factors up there to be a perfect square. Because if I take the square root of a perfect square, I should get a whole number. So we are looking for numbers that, when we take the square root, we get a whole number. The square root of 4 is 2. The square root of 9 is 3. It's an exact whole number. The square root of 2 comes down to 1.414. The square root of 3 comes down to approximately 1.732. We don't want decimals here. So we have a list of perfect squares. Up through 10, we have 1, 4, 9, 16, 25, 36, 49, 64, and we can go up through 15, 121, 144, 169, 196, and 225. Now, once again, I'm sure at some point I've alluded to this, but just going back for us math nerd people that like to see patterns of things, like I thought it was pretty cool that Tuesday was 4, 2, 2, 4. 4, 2, 2, 4. I tuned into that real quick. I thought that was pretty cool. Now, even though 0 is not a perfect square, if I would throw it up here, because 0 times 0 is 0, if I take the square root of 0, I could say it's 0, but there's more than one thing I can multiply to get 0. To go from 0 to 1, I would add 1. From 1 to 4, we would add 3. 4 to 9, we can add 5. 9 to 16, we can add 7. 16 to 25, we can add 9. 25 to 36, we can add 11. Then 13. And I can continue that through on indefinitely. I add 15, I add 17, I add 19, I add 21, I add 23, I add 25. We add 27, we have 29. And to get to the next one, we can add 31. So we had 29 here, so 31, so the next one would be 256. Then we can add 33 to get 289. Then we can add 35. So it's a pattern that you add the next odd number to get to the next perfect square. And that will go all the way through all the perfect squares as we go through that to infinity and beyond. So if we take a look here, we want to break square root of 24 down and simplify it down. So we want to find two things that we can multiply together. And I'll break this and slow this down here. Two things that we can multiply together 24, but we want one of those things to be a perfect square. So Brady, what would that be?
Square root of 4 and 6.
Okay, so we go 4 and 6. Now, I'm slowing your brain down because I know what we tend to do is we go from here down to the next one, square root of 4, square root of 6. And what we are applying here in our brain, we're applying this property here, which will then give us a value of 2 square root of 6. Square root of 72, go ahead and break it down. Simplify square root of 72 down. Now, some of you may have broke this down into square root of 9 times 8, because 9 times 8 is 72. 9 is a perfect square. So we want square root of 9 times square root of 8. So we have 3 square root of 8. Okay? And that's correct to a point, but we are not fully simplified. Let's see. That'd be like saying 12 over 42. I take 2 out of top and bottom and give me 6 out of 21. But we're not fully simplified because we can still divide by 3 to give me the value of 2 out of 7. Well, when I go down to 9 and 8, I get 3 times the square root of 8. But square root of 8, I still have a perfect square factor of what, Jacob? Okay, so we have 3 times square root of 4, square root of 2. So we have 3 times 2, square root of 2, or 6 square root of 2. Now, some of you may have saw up here, I can just go square root of 36 times square root of 2, which then I would add 6 square root of 2, it would fall out 4. Well, when we're dealing with squares and perfect squares and square roots, when we take the square root of 64, we get a value of 8. And going back to definitions of square roots, the reason why we say it's a value 8 is when you go through the process of taking a square root, you're looking for a value that you can multiply by itself to get the value underneath the radical. So 8 times 8 is a value of 64. 9 times 9 is a value of 81. A value you can multiply by itself to get the value underneath the radical. But when we have the square root of -4, if I take -2 times -2, do we get -4? No, we don't. So what we have to do is we have to remember a nice little idea, and we talked about this in the first semester, is the square root of -1. We cannot take the square root of -1, but what we can define that to or as is a value of, bless you, an imaginary number. So square root of -1, we get a value of I. And when dealing with the square roots of negatives, to be able to simplify this down, the first thing you want to do is you want to take out the i's. And how we take out the i's is we can simplify this down into square root of -1, square root of 4. Square root of 4 we can do. Square root of -1 we just define it as I. So we get a value of 2i. Square root of -32. Okay, you want to simplify this down? First take out its I. Typically, when I see a negative with a radical, I just throw an I out, then I have I square root of 32. But to further break this down, we can break this down to square root of -1, square root of 32, and that leaves me the square root of 32 that we want to simplify down. Once again, this is something where, yes, 4 will come out, but you have to make sure you fully simplify it down. Or you can find a bigger number, it's a perfect square, or 32. Emily, what can we break 32 down into?
2 and 16.
So we have 16 and 2, so we have I times 4 square root of 2. Now, how we write this? We can write this as 4i square root of 2 if we want to, or 4 square root of 2i would be also acceptable. Okay, you can throw the I in between, you can throw the I after. If I have two imaginary numbers and add them together, if I have 6i plus 4i, Okay, think of the I as the variable. 6i plus 4i. What do you think that equals? 6i plus 4i. Seth, what do you think?
Radical negative 36 plus radical negative 16.
But if I have 6i plus 4i, or if I have 6x plus 4x, what would that equal?
10x.
10x. So if I have 6i plus 4i, what do you think that equals?
10i.
10i. There we go. You would have eventually got there, but you would have got to Worcester. You would have got to Worcester from Downton through Richmond, maybe Cleveland. But we would have got there. But we'll ease our pain here a little bit and just we'll add our coefficients together, give us 10i. Well, if I have 6i times 4i, well, if I have 6x times 4x, we had 6x times 4x, what would that equal? 6x times 4x. Jocelyn? 24x squared. So if I have 6i plus times 4i, what would we come up with? 24i squared. Now we take a look at this I squared. Taking a look at the I squared. That means we have the square root of -1 that we are squaring. Well, if I take the square root of -1 and square that, what would we come up with? What would we come up with there? Micah, what would we come up with? -1. So I have 24 times the value -1, which would give me -24. Which goes into the old adage, going into the Barney world again. I have two numbers that live in the Barney world, two imaginary numbers. And when they multiply together, we get a real number. Now, I think BJ and Baby Bob are brothers and sisters, if I remember back. So that's sort of a sick thing to think about. But if we would take two entities from the Barney world and they would multiply and have kids, does that mean all of a sudden a real person would pop out somewhere? Sort of cool. Where'd you come from? Well, I came from the Barney world. We'll put that, that's just theory. All right. We will finish up our notes tomorrow. You have nothing for tonight. I'm sorry to disappoint you. You have nothing for tonight. We'll finish up complex numbers tomorrow. Hopefully give you some time here within class to be able to start your homework and get it going. All right. Questions you have?
I got a couple of